needed space contains the information of all of the nodes, because we need to increase the length of the queue to capture all of the neighbors. Because of that, we need in this queue, we count the number of nodes, Bm. B power m as the needed space. This is very, very, very greater. Greater than Bm. And the worst complexity when the goal is in the rightmost child, you need to check all of the nodes. Similar to DFS, the worst complexity is OBM. Similar. And the optimum. Yeah. If the goal is the first level, you can find it in the first iteration. If the goal is in the second level, in the second iteration can be accessed. Because of that, this is optimal. Is it complete? Yes. Because it can find it complete. And the third one, as you remember, in the third implementation, in deeping strategy, we combine both of the approach. The computational complexity are the same, not important to combine. But the space, this algorithm is better than this algorithm. Because of that, we try to increase this approach to the BFS. Because of that, we limit our attention limit 1 or level 1, check by DFS, and increase the limit 2. Increase it, again, check it. But the information that is saved in this algorithm is similar to DFS. For example, this branch is need to save. If the goal exists, stop. Otherwise, another branch. If the goal exists, stop. Otherwise, check the next. Again, B type should be checked. The head of any branch is O M. Head of a single branch. B cross M O M. B needed space for DF, iterative deepening. This is iterative deepening. I said a queue again, a queue containing all of the nodes in limit 1, all of the nodes in limit 2, etc. And the needed space is similar to DFS or BM, similar. And computational complexity, the worst case is remain in the rightmost chart. For the iterative dipping, again we need to consider this node to get the goal. Because of that, the computational complexity is similar. Is it possible to find optimum? Yeah, because it is similar to DFS. Similar. And calculated, yes, okay, you can find it. Now, in all of these algorithms, we assume that the cost of links are fixed. Because the cost of fixed BFS and iterative dipping can find optimal solution. Because they enumerate just the links. I enumerate one link. If there is a goal, the optimal cost is 1. If the goal exists in the level 2, I take all of the nodes. The cost is 1 plus 1. 1 plus 1. You gain 1 plus 1. For all of these nodes, the cost is 2. But now we consider some graphs, some weighted graph or network? Weighted graph or network containing non-negative cost for links. I can define the weight for the nodes, but any node can be transformed to a link by adjusting two nodes and a single link instead of a node. Because of that, it is not necessary to consider both of the link cost and node cost. If you have a node whose cost is 8, you can transform this node to a pair of nodes without cost and copy the cost for link 8 as the link cost. Because of that, it is not necessary to define two different problems, one of them containing cost for nodes and one of them for links. If you face with some problems containing the cost for the nodes, you can transform any costed node into a pair of nodes and transform the node cost to the link cost. And non-negative. Non-negativity is very, very important because for terminating the algorithm, we need to this important assumption. But in real problem, is it possible to extend our knowledge about negative cost links? Yes, it's possible. But the algorithm is more complex. Because of that, we start with this assumption until this lecture, the end of lecture. Now, we have a network containing positive links, maybe some in the zero cost, not important. Negative cost is a drawback and cannot solve the problem? No. But non-negative, including positive or zero, is a good idea for us. Now, similar to this discussion, we need to define a reasonable data structure for saving such networks. For saving such networks, instead of a stack, queue, we need to define a more modern data structure because the cost is a very, very important topic in this part. Follow in DFS, DFS. I presented our outline from the left side children. But instead of leftmost child, you can focus on the rightmost child. It's not important. In this stack, the order of this node is reversed. In this stack, I say the rightmost child. First. Rightmost child first. And then the middle is saved, and then the leftmost child is saved. If your strategy is reversed, and you need to change the rightmost branch, you change this order. First, you save the leftmost child, then middle child, then rightmost child. Similar to the previous implementation, you can define the rightmost branch at the first, at the cheapest branch. Now we are focusing on the cheapest branch. Group say that you need to define a priority queue. What's priority queue? Huh? What is priority queue? In a priority queue, instead saving the nodes with left to right or right to left order, you assign a cost for any node. This is name of node. And another array containing the corresponding cost. For example, you say A, B, C, D, E, F, G, H. And the cost is 9, 4,
5, 5, 3, 2, 1.
5, 4, 3, 2, 1. Enough. The greatest cost is saved in the top. Front of Q is the best. When you need to pop or remove any member from the queue, you need O1 for removing, because or DQ, because you try to ignore from the front of the cube. But if you receive another node, for example, G, with the corresponding cost 6. At the first, you need to find the best location for this one. You need to define a search or a binary search to find the best location for 6. If you use common search, need at most n operation to find the location, because you check 6 with 9, 6 with 5, 6. The 5 and 9, the best location is this one. But in the worst case, you need to check all of the members in the array. Because of that, in the common search, you need n operation. If you use binary search, you need to combine or like n operation, because at the first you check the middle of the array. Your k exists in the first part or the second part. One of the part is ignored. Half of the information is not needed to consider. Again, in this part, we check the process. We check the middle. Again, in one of the parts, we first with the k. The other part is left. Our focus in this part. Again and again, you try to check n over 2, n over 2 top 2, n over 2 power 3, n 2 power 4, until receiving a single node. When you receive a single node, you come back, you find the solution. This process needs like an iteration. O1 for removing or DQ, O like N for finding best location. Now, if you use array, when, for example, find the best location there, you need to exchange these cells to the next cells to get a free space in the middle of the array to insert the new data. Because of that, for adding a new member, two operations is needed. One, for finding the best location, that means O like N. And you need another operation for exchange changing the location. It needs ON because in the worst case, you need to remove this one and this one. Until end. This is O N. Yeah. In the worst case, you need O log N for finding the best location and O N for exchanging the location to be a free space for adding the new member. But if you define a class for node containing name or index, and the cost, and define a linked list O1. For finding the best location or log N. And for add, you need O log N to find the location. For example, this part. And instead of exchanging the location, you disconnect this one, add a new connection between these nodes, yeah. O1 plus O1, again is O1. Add O log N for location plus O2 for disconnecting the previous link and adding new links. This is O log N. This means that implementation by array is increased your adding cost, but by using the linked list as the infrastructure for saving the information of the node, you can decrease the amount of the adding process to O log N. Come back. We have a weighted graph containing non-negative costs. We define some nodes. In the node, we say the index or name of the node and the cost, and define a linked list containing the information of this class. Now, continue to solve the problem. From S, I define in my linked list node S with cost. Cost 0 is better because we assume that all of the costs are non-negative. Because of that, the 0 is the candidate for the best cost. If there is some negative cost linked, it is possible to define some example that can define a path from source to the target with negative cost. Because of that, we cannot define 0 in this place. But because we focus on negative cost, as the links. We can define S with 0. I write 0 as the cost of pass from S to any node. S to S, 0. The cost is 0. Its child is D, E, and P. I define a temporary memory. Instead of saving the information in this part, I define temporary memory. Temporary memory. I write S child. S child is D, E, and P. And evaluate the cost from S to D. S to D is 3. Yeah. For E, S to E is 9. And the cost from S to P is what? In the linked list, based on the priority, I can register from the greatest to the least, or from the least to the greatest. Which of them is better? I need the cheapest one, because I need the cheapest one. This is the first, this is second, and this is the third. In the linked list, I define P with 1 and D 4 with 3, and finally the E with 9. The last one is 9. Now, S is marked. S is marked. I can delete it with O1. This is the start of priority queue. Again, I consider the first one because in the priority queue, we just access to the front of the queue. P is common. I create the temporary memory. The child of P is saved. Child of P is Q, just Q. And the cost. The cost from P to Q is 50. This is C, P from Q. But I need the cost of pass from S to any node. This is added with cost of P. Cost of P is 1 equal to 16. This is temporary. We need to find the best location for this one. I call binary search. The binary search try to find the best location for 16. The best location is this one. With O1, I add and you know containing Q with the cost 16, and this is node. This node is marked, and I remove it from the priority queue. As you see, S started, P is better, P checked the child, 16 is obtained. Now, between 3, 9 and 16, in the front of the queue, we face with D. We left previous pass. The previous pass should be checked next. Now we focus on D. And from D, again, in the temporary memory, I said the child of D, B, C, and E. B, C, and E. B, 1 plus the cost, 3, equal to 4. C, 8 plus 3, 11. Next, E, 2 plus 3, 5. Again, by binary search, I try O like N to find the location, best location for B, C, and E. For B, for between this node and this node, B with 4. Or what operation is implemented? Again, for C, 11. 11 between this node. Again, I add a new object, C, 11, and disconnect this connection and add a new connection. And E, again, looking for E, 5, disconnected and connected to this node. O1. As you see, adding just O like N, because disconnecting and connection is implemented in O1. We check the best one, D, and D as for children. Cool. Now, D is marked and we remove it from the priority queue. We continue from the front of the queue, B. Call the neighbors of B. Neighbors of B is A. Sorry. Neighbors of B, A. Anyone? No.
No.
There is no.
No.
The cost is 2. 2 plus cost of B 4. 6. We have again binary search is implemented. Find the best location between this node and this node. Again, I added A with 6 and connect themselves. B is checked. I remove it from the priority queue. Now E. E is in the front.
2.
Again, I count the child of E. What's the child of E?
2.
H and R. H and R. What's the cost of H? 8 plus 5 equal 30. 4 and
2.
2 plus
5.
5, 7. Again, by using the binary search, I find the best location for H, 30. Between this one and this one. H with 30. By O1, I improve the links. And for R, 7.
7.
7 after this one.
Okay.
Again, R with
7.
Correct the connection. E is checked. I remove it from the priority list. A is in the front of the queue. I choose A and again cut its neighbor. What's the neighbor of A?
2.
No one.
No one.
No one. Because of that, I say that A is checked. There is no child in the temporary memory to add. In the front is
R.
the child of R
F.
is F. The cost 1 plus 7. 8. I add a new object containing F and 8 and correct the connection. R is checked. I remove it from the list. F is selected. G and C. Yeah. G and C. 2 plus 8 equal to 10. C.
A.
F to C. Cause F to C. F.
C.
Where is F?
No F. A.
This is a single. Yeah. Yeah, it's a single. Yeah. I add G. G 10. By binary search, the best location is between 9 and 11. I add a new object containing G and plus 10 and I remove it from the list. Now E is in the front. Because of that, I need to check E and its label in the temporary memory. I check E. Now, what's the label of E? H and R, yeah. H and R. The cost H 8 plus 9. 17 and R 2 plus 9 11. By using binary search, I try to find the best location for H. H 70. 70. The location is there. H with 70. And R 11. 11 before or after C, not important. I add in this part R with 11, connect it, and something there. That's important. The order of C and R is not important. For simplicity, I connect it, and this one, and this one. E is checked. I mark it and remove it from the
So G.
priority queue. G is fine. We stop.
G.
Although G is found in previous steps, but we don't stop and try to find different options, because maybe you find G with cost 10, but other options in the, for example, the neighbors of B or the neighbor of E, A, R, F, who are less than 10, one of them, for example, F. Maybe from F with cost 8, you can define some type to receive to G with 8 plus a positive number. A positive number. Positive number with respect to the cost of these links. Maybe 8 plus positive number is less than 10. Because of that, we check another possibility for going from F to its neighbor. If there is no option less than 10, similar to this example, after several marked node, we receive to optimal node with the best option and the best cost. Because of that, if I add a row to this one, writing uniform cost search or UCS. Data structure is priority queue. Data structure is different. Needed space. What's the amount of the space that is needed by yourself? Oh? No. Less than. Remember? I have a link list. In this link, I started from one object, then add its neighbor, and the neighbor of the neighbor, etc. This link list contains at most all of the nodes. And at most all of the nodes. Because sometimes we need less than this. If a node is repeated, we compare the cost. For example, if there is another way to go to E, I check the new cost with 5. If the new cost is greater than 5, I know from the new computation. I say that I have better option. If I find another option with less cost, I substitute the less cost instead of previous cost. Because of that, at most O, N, number of nodes. Is needed to say in a priority queue. This is less than this one. And in the most case, less than here. This is always less. It is usually less than here. Because of that, UCS is the best option for needed space. For the computation complexity, in the worst case, again, you should to check all of the nodes to find a node with the least cost. Because of that, unfortunately, the computational complexity is OBN. In the worst case. But in real implementation, we can decrease this one to O, N, log N. We can improve it because we have at most N nodes. For finding the best location for any node, I need log N operation. By multiplying N in log N, the complexity is O N log N. Instead of this computation file. O N, the number of nodes, cross O log N for finding the best location in this very, very important data structure, linked list. Priority queue with linked list. If you use linked list for implementing priority queue, you need at most ON member. For finding the location of any node, you need O log N. The multiplication of N log N is the final complexity. And is it optimum? Yes. Under the non-negative cost, the path is optimum. But if there is some negative cost, for example, this is, for example, A, B, 2, A. Go. It is a counterexample containing a negative cost for a single node. You started from S. The child is A and B. The labels are 2 and 8. 2 is better, you choose A. The child is G. The cost is 1 plus 2. 3.
3.
You compare 3 and 8. 3 is better. It is in the front of the priority queue. You stop. But it is not optimal because you have another pass with cost -1 to receive to G. As you see, the optimality is dependent on the non-negativity condition. If you consider an example with negative cost, this algorithm cannot find the optimal solution. This is counterexample. And this is completeness, yes, based on non-negative cost. Again, this algorithm is not negative. Please check with 4. 4 is the list. Now, between 6, 11, 5, and 16, which is better? A with 6, E with 5 is better. The child is H and R, 30, and so on, and continue to find a solution. The fringe. What's the shape of fringe? In the DFS, the fringe contains some branch. In the BFS, the fringe contains some levels. In the iterative dipping, similar to BFS, the fringe contains some levels. But in the uniform cost search, in the first one, the set contains the node with the least cost, S, with cost 0. Next, the nodes containing the cheapest cost. The cheapest cost is 6, 4, 3, and 1. That's colored by yellow. We extend our fringe. The grid one, containing greater cost, 9, 30, 7, and 8. Again and again, with respect to amount of the cost, you increase the fringe. It is very, very different from the fringe containing branch and containing some levels of the nodes. The reason of the success of this algorithm is dependent on choosing very, very intelligent fringe in this example. Our book don't use from the linked list, and because of that, it tries to search more options. As you see, all of the nodes in the tree is searched by with respect to cheapest nodes. In the book, assumes that the best cost is C star, and the height of the optimal path is epsilon, and approximate the cost of the link by the C star over epsilon. But it is not efficient algorithm, because as you see, the memory used by our book is O B power C star over A. But my implementation based on the linked list needs at most O N for saving the information. It is better than the book, because this is an advanced data structure. When you use an advanced structure, you can improve the quality of the algorithm. Please pay attention to the difference between the material of the book and what I said in the class. I focused on the priority queue based on the linked list, but the book saves the information in the set. As you see, in every step, the book saves all of the information in a set. Because of that, for choosing the next option, it compares all of the labels. For example, in this example, 11 is compared with 13, with 7, with 9, with 16. 5 comparison is needed in this example, in this iteration. But when I use linked list and implemented the priority list in linked list for choosing the next node, I focus on the front of the queue, just front of the queue. O1. That is better than the implementation of the book. Maybe I use such implementation in the final exam. You should implement the efficient way for the problem. And the fringe is presented with B power C star over E over epsilon. But my implementation is more efficient because I try to check the minimum part of the node for getting the final information about the optimal path. Is it optimal? Yes, it's possible. It's possible. Please remember this important sentence. We say cost of a path from S to any node. S from to any node. But we don't have any approximation from the cost from these nodes to the target. Or goal. We have not any information about this. As you see, A star as registered in the last sentences, we have an approximation about the node to the target. We combine this cost to choose the best option for continue. This is the meaning of informed search. Informed search means we have some approximation cost to travel from any node to the target. Informed search in this section contains just this information. The cost from source to any node. All of these labels is the cost of travel from source to P, to D, to E, to G, to Q. In the next section, when we approximate the cost of path from the any node to the target, we present a new kind of the algorithm named A star to find the optimal solution of the network with respect to a heuristic one approximation to approximate the cost between the current node to the end node. That's enough. I'm ready for your question. Just ask me what is the question. No problem?
No problem.
Thanks so much.